All right, so how's everyone doing? It's 4 o'clock and we've been going since 8 o'clock. Is everyone doing pretty good? All right. So this is the Enable IoT talk. So my name is Jared Rhodes. I'm an MVP for Microsoft Azure. I'm also a Pluralsight author. And this is my email, blog, GitHub, and Twitter. And if you need to find me on any social media, this is the pattern that you can find me. You can use to find me. So I've got a Pluralsight course coming out. It's identify existing products, services, and technologies and use for Microsoft Azure. It should be published by the end of the week, but we'll see. It's currently complete and in review by Pluralsight. All right, so our agenda for this talk, we're going to first talk about why is there a surge in artificial intelligence. Then we're going to discuss what is deep learning. Then we're going to take a look at the Azure IoT Edge platform. And then we'll take a look at cognitive services. So the reason I want to talk about what is deep learning before we get into the Azure IoT Edge is so that I can sort of get your mind prepared for what the compute looks like once we're on the edge, because a lot of people will think of a Raspberry Pi. And then they'll try to run it as sort of a multi-camera video stream processor to detect images in vehicles and stuff like that. And I want to discuss what is deep learning and what it looks like computationally before you go down that path. All right, so first, let's talk about the surge in AI. So
Back in the 1990s, the investment that was being put into AI had been pulled back. Basically, in the 80s, people were, the movies were coming out, Terminator, blah, blah, blah. Tons of money were being thrown into research for AI, hoping for that next big break. By the 1990s, since there was no big break, all that money had been starting to pull back, and most of the research was just being data-driven, just your standard best fit curves and decision trees, nothing truly as advanced as we see now. In 1997, IBM's Deep Blue beats the world champion at chess. I'm sure you can all remember that from all the commercials and stuff that were coming out at the time. In 2006, we have the major event. So Geoffrey Hinton and a few others, they coined the term deep learning and explain algorithms that can let computers see. So this was the big breakthrough in AI that sort of quietly happened. They were able to showcase how you could use deep neural networks to detect features within data sets and then use that for predictions. Because of this, by 2010, the Microsoft Kinect could track 20 human features at a rate of 30 times per second. In 2012, the Google's X Lab developed some machine learning algorithm that's able to autonomously browse YouTube videos and identify them if they have cats. By 2014, Facebook develops DeepFace, software that's able to recognize and verify individuals on photos to the same levels as a human. And then in 2016, the Google's artificial intelligence algorithm beats a professional player at the Chinese game board Go. One of the important things about beating the professional player at Go is that Go had enough permutations. Basically, you couldn't brute force the tree down to see all the different ways in which the game could go. The algorithm, the machine learning had to learn the features of the game to understand its next steps. It couldn't really programmatically try to figure it out through a decision tree. Here's a nice hockey stick graph to show you that AI is going to be worth a lot of money. But yeah, it's supposed to be, obviously, as we've all seen it, there's huge investment going from both vendors, customers, and then developers all trying to get into AI and seeing the growth in that market. One of the reasons you see it is it's a perfect opportunity for the cloud vendors, right? If I can sell you on AI as a cloud vendor, you're literally paying me to run through millions of cycles of compute time to try to make the algorithm stronger, to have better predictions. And some of these pay-as-you-go, $3,482 per month for some of these. These are big. They carry the big GPUs, which are coming from the vendors, who are also getting into this market due to the price. So if you want one of the Teslas from one of the machines I just showed, so the Tesla V100 from NVIDIA, You can get it for $19,000 from Dell if you'd like to get one. If we go back, some of these machines are running 4 of them. You can also get the, that one. The Tesla M60, blah, blah, blah. You can get that one for $4,587 if the $19,000 price point was just a little bit outside of your range. You can go for the AMD version, which is $4,399. So this is a great opportunity for all of the silicon vendors because you're selling $20,000 graphics cards. And then we're getting into custom silicon like FPGAs. So FPGAs are circuits that, programmable circuits is the basic way to put it. They're made more for signal processing. So don't think of it as a sequential step. You program logic gates and the signal gets processed through the logic gates. The best project I've seen from it is, most people don't know, the HDMI cable is encrypted. So the signal that goes through HDMI is encrypted. And I saw a project where someone used an FPGA to actually write onto the encrypted stream of an HDMI cable so they could plug it in and they would have an overlay onto their screen. So they just had a little custom dashboard for their TV. That's what FPGAs are for. They can actually, much more efficiently than a GPU, write onto a stream. And you're seeing them pushed more and more with Microsoft Azure's Project Brainwave and other vendors are using these FPGAs in machine learning because of their ability to process at a level of an order of magnitude better than GPUs currently. We've got Cognition as a service. So Cognition as a service is basically the things that we would think of for deep data, deep feature sets, vision, so seeing things, detecting objects, detecting where they are, detecting what's in a picture, speech, knowledge, those kind of data sets, language, that have deep features that need to be understood. Some of those are solved problems now. In other words, each vendor can sort of take a solved solution and create a software as a service for you. So you have Cognition as a service, and there are multiple vendors that have products available for you to just use out of the box. Excuse me. So the explosion of machine learning has sort of changed how we think about solving certain problems. So this is an XKCD where someone is asking for an application. They want to know where the picture is being taken, and then they would like to know if there's a bird in that picture. And in this one, he says, I need a research team in 5 years. So that was actually published in September 24th, 2014. It hasn't been 5 years yet, and now being able to detect if a bird is in a picture is quite trivial, and we'll actually look at a similar use case as a demo. So not even in the time he thought he would have a research team to do that, you can now do it out of the box. So looking at deep learning, and this is me trying to set the stage for once we get into edge computing. So what is deep learning? So the primary way to do deep learning is through a deep neural network. So deep neural networks have an input, an output, and a number of layers in between. So each one of these, if you look at the yellow dots and then the orange dots, every yellow dot connects to every orange dot. That is a fully connected neural network. What that means is every time this neural network has to process data, each one of those connections has to be processed. They have a weight and a bias. And you are going to put data into that function. So each connection is a function, and we'll go into what those functions are. And you have variables within those, usually just a weight and a bias. You know the answer to the question. You're going to feed that into the neural network. So you know the output. And what the algorithms are going to do for you in the libraries and whatever you're using is they're going to walk backwards through all of these connections. And if it's predicting properly, it'll strengthen that connection. So in other words, it'll increase the weight and the bias. If it's not predicting correctly, if that's a connection that does not predict the data, then it weakens it. And if you look on the second picture where all of the fully connected layers, it's showing the route of a correct prediction. Once we've trained it, then we have dropout. We have neurons that are no longer involved in the decision making. Now every time you plug in data to the yellow layer, it has to compute every single one of those, but some of these data points are no longer useful, so they drop out. And that's how it does deep feature detection. I know that's a lot. If you don't know anything about the neural networks, that's a lot to throw at you at once. We'll go through a few more things, and then we'll take a look at a neural network example online. So I told you that each one of these connections is a function, and they are. That's f of x of something with your weight, usually times your input plus the bias. And you decide what your activation function is going to be. So an activation function is, again, it's f of x. So you're deciding what function you're going to operate on in that connection. So you plug in data. Let's say you have just the function and it's weight times your data plus bias. If we choose something like a rectified linear unit, what we're looking for is dropout. So it's just a function that basically says, if this is a negative number, make it 0. If it's positive, keep the positive value. So we're looking to drop out neurons as we process this data so that we can discover the deep feature set. And that's going to be really hard to see, I assume. But those are the different graphs of the different functions you can choose, and if you create machine learning models, you'll understand there's different use cases for different functions, and then sometimes it's just throwing darts at a board to kind of see if it works. And then as it optimizes, there is a learning rate. So we talked about you have your weight and your bias, and it back propagates, meaning it goes back and it adjusts those weights and biases to correctly fit to your data. The learning rate is how much it adjusts those, and then optimizing is, as it walks through the tree and adjusts each of those weights and biases, is trying to look for a global minima. So I'm just pointing this out. When you optimize, training takes a while, and the reason it takes a while is if you pick a high learning rate, you can fall into, you can do it with a low learning rate too, but if you pick a high one, you can fall into a local minima and you won't actually have the correct weights and biases for your model. So let's try to take a look at something Google has online to help us better understand or better visualize this data, or these neural networks. So in this one, I'm going to now drive with my mouse and try to circle things for you. So in this one, we have a data set, and in that data set, using that data set, we're going to plug it into a neural network. So in this neural network, you'll notice that if we increase the number of data points, the number of connections increases by the number of neurons in the next layer. So again, fully connected, every time each one of these is processed, you have to compute each connection. So if we look at these, this is the very nice visualization because it shows us that each connection has its own weight. It'll also have its own bias as well. And as we go through, we can add a number of layers, outputs, and connections, however we'd like. We can choose an activation function. So each one of these changes what the neural network looks like under the covers. So if I decide to use a ReLU function, whatever the data input is between this neuron and this neuron is the ReLU function of that weight, 0.23, times whatever the input is between those neurons, or the input is for x1, plus whatever the hidden bias is. And as I train, so let's pick a learning rate, we got the ReLU function, let's just train, and as I train, these weights will begin to adjust to best fit that data. And then after it's trained and it's accurate enough, we have a fully trained neural network that we can deploy into production. Is everyone still with me up to this point? All right, the primary reason I went down that whole rabbit hole was so that you can understand that each one of these has to be processed. And if I put a deep neural network for something like image processing, which doesn't just use fully connected layers, it'll use partially connected layers and other neural networks within it, that's a lot of processing if you think about trying to process every frame in an image or something like that. So we're going to talk about the edge platform, but understand that if we're trying to shove these machine learning models onto this limited hardware, it's not going to work. All right, shifting gears completely, we'll go over the Azure IoT Edge runtime so that we can talk about the edge computing. So we've got IoT in the cloud and we've got IoT on the edge. What are the differences besides one being in the cloud and one being on the edge? So in the cloud, obviously, we can do remote monitoring. If the thing's connected to the internet, a lot more possibilities open up. I can send emails when there's a fire, just little things, right? I have more possibilities since the device is connected to the internet. I can merge remote data from multiple IoT devices, meaning I can have an actual look at an entire data set as opposed to just the data for one device. And then the normal cloud thing, as long as I've got money, I've got compute power, right? I can just throw money at my problem, and I have infinite compute resources behind it. So why don't we want that for every problem? Well, we've got IoT problems on the edge, like low latency. So what I normally do in some of these is I have this video, there's this saw, right? Saw, you cut wood. And when your finger gets right up to the saw blade, the saw will disengage and stop. If that saw blade has to connect to the cloud and send the, hey, there's a finger in here, it's not a good device, right? It's like the half a finger solution. So that low latency for a lot of problems is very important so that you don't end up with just problems, whether it be machines, your actual physical infrastructure being damaged, your users being damaged. Protocol translation, so a lot of the work I've done in IoT has been things that were made before I was born, right? Things that were put out into the desert in the 1970s that use protocols that are no longer supported for most major hardware, and you have to connect that to something that'll then talk to the cloud. So protocol translation and data normalization so that I'm not trying to send up sudden burst packets, I can spread it out. Or if I've got a temperature sensor in a room like this, I really don't care to know every second that the temperature is whatever it is. I just want to know when it changes. Privacy and IP. So yeah, a lot of companies don't like having all their stuff in the cloud, especially if they feel like they're a competitor with the cloud vendors. And then intelligence at the edge. This machine learning stuff that we just went over, not only is it hard to compute on a device like a Raspberry Pi, it is also expensive to continually compute in the cloud. So sometimes you just want to take that computation and shove it on a device that you don't have to pay to use by the hour. And then obviously offline operations. These cloud vendors are great. Sometimes they have outages. And you have to have some way to make sure that, that saw doesn't just all of a sudden go, well, I don't know, I can't really, no one's telling me to shut off, so I'll just keep spinning. All right, so the design principles, I'll go through this quick. It's supposed to be secure. That's the number one thing. Every time you read the news with the letters I, O, and T in it, it's a security breach. Rarely do they put IoT in the headline when it's a nice, cool new product. It's always a security breach. So the IoT Edge platform is security first. It's cloud managed, and we'll actually go and we'll look at the cloud managed features of the platform. It is cross-platform. It supports Windows and Linux. And technically, according to the team, if you really, really, really want to, you can build it from source and run it on RTOS or any other thing you want, but we're starting to get into some mixed worlds to where you're just doing it to do it. It's portable, so you can do things in the cloud and on the edge with CI/CD pipelines and all that without having to worry about whether it'll work on each. And it's extensible. It's container based. We'll get into that. It's container based. If you can put it in a container, you can put it on the edge, and that pretty much is everything. So the concepts, it installs and updates workloads on the device. It maintains the security standards. It ensures the modules are always running. It reports the module's health. It facilitates the communication between the tiers of the edge gateways, and we'll go over that in a second. It facilitates communication between the modules on the devices, and then finally, it facilitates the communication between the device and the cloud. So there are different ways you can connect the devices in Edge to the cloud. In fact, if we're thinking about an IoT deployment, there are plenty of different ways you can set up these connections. So one is a direct connection. That's the one you use in most demos. You just take a device, you connect it directly to the cloud, and then you just start sending messages. And whatever your ingestion engine is in the cloud just absorbs those messages, and now your messages are in the cloud. What you can do in other situations is you can use a gateway. For what I was talking about where things were made before I was born and you have to connect it to something to translate it to the cloud, you can use a gateway, and that gateway will take in those messages and then act as a singular point to talk to the cloud or whatever your ingestion engine is. So in this case, we have all the different things I just talked about. We can rate limit, we can look at multiple messages from multiple devices. It's much more robust than just connecting directly to the cloud. You can also connect gateways to gateways, right? Now we're getting into the you can do whatever you want scenarios, right? You can have a gateway in one field that connects to a radio tower that connects to a gateway that acts as an aggregate for all the ones within range of that radio tower, et cetera, et cetera, et cetera. So this way, each gateway understands every device downstream. In other words, when you program, that gateway up here does not see this gateway. It doesn't understand there's a gateway there. What it thinks is that these devices are directly connected. And then in the same, if you want to connect everything to the cloud, you can set it up to where every device connected, whether it's direct or through a gateway or through a series of gateway, that's all removed from you once you start actually using it. Every gateway will see those devices as directly connected. And whenever you want to use those devices, whether you're sending messages, absorbing messages, you don't have to worry about all the different infrastructure in between. So the actual Azure IoT Edge runtime. So the runtime consists of two major components. You have the Edge agent, which is managing your device or your gateway. And then you have the Edge hub, and the Edge hub facilitates the communication. So the Edge agent instantiates the modules, and we'll get into what the modules actually are, but basically they're containers. So it instantiates modules, it updates modules, it reports the module status, and it restarts modules. Basically, it manages the modules. So a module image, it's a package containing the software that defines the module. An instance is the instance of that image. So who here knows containers? All right. So it's a container, right? There's an image. When you deploy it, there's an instance of that image. The identity is the actual security credentials and information stored to make sure that it's that module. And then there's a twin. So whenever you want to manage your container on the device or your module on the device, there's a twin that sits in the cloud, and all you do is you send a message to IoT Hub. You say, I'd like to update this property, or I'd like to call this function. And that gets passed from the cloud down to that device so that when you program your device, all you see is those updated properties coming in or those functions being called. This is the actual workflow. Hopefully this is a nice, beautiful graphic to help you understand. So when we get started, we're going to open Visual Studio Code. We downloaded the extensions. We're good to go. We want to create some modules. So we open Visual Studio Code. First thing we do is we create the module, which is basically just a container. Then there's a container registry in the cloud, so we're going to upload that container to the container registry. Then in IoT Hub, we're going to tell it about this container. And we're going to create a manifest that understands that in a edge runtime, this container is supposed to be there. Once we tell it about that, it will then update the manifest on every device that is running that, I don't want to say just that container set, but basically the one you've defined for that manifest, because you can have different manifests running on different types of devices. So once you say, for these devices, I want this container on there now, the IoT Hub, once it sees that that's valid, it'll tell every one of the devices on the edge, hey, it's time to update. So once they get their updated manifest shipped to them from IoT Hub, then each of the devices goes and it looks at that container registry, and they download those containers and add it into their edge runtime appropriately. Does that make sense? Does everyone follow that? Because that graphic took a long time to make, so I hope you all followed that. All right, so once you get that module or that manifest update and it starts going through that workflow, you actually get updates as to the module status. It keeps reporting that to the cloud, and you can hook into that and look at it. It's either downloading, it's unhealthy, it's failed, it's stopped, or hopefully it's up and running and it's a part of your workflow. The module twin, which I talked about before, allows you to do tags. I'll go back. The module twin allows you to do tags. So the tags are basically a way of you saying, just for an example, retail customer of mine, they make the hardware, they sell it to the retail customers. I mean, if it's Kroger, I just tag all the devices that are for Kroger with the Kroger tag. And then when I go back and I need to do a query against IoT Hub, and I only want to do it for that customer, I just query by that tag. But you can do other things. You can say, this is my temperature sensor, this is my video processor. It's just a tag, it's a string you're going to attach to this. It's a string you're going to attach to that document so that you can then query it later. You have desired properties. So the properties on the device, to give you a use case, I had one that was a connection string. So all the connection string was, we could update the connection string and it would connect to a database on the local network. And so I put that database as a property, and then every time a device got deployed where there was some different parameters on that connection string, we would just update that property and change the connection string for those devices. The desired property, sorry, I'm trying to get this mic to stop making that sound. Can you still hear me? Okay, hopefully that's better. So the desired property is what I want the property to be. The reported property is what the property currently is on the device. Those two can be out of sync because when you update a property, you have to ship it to the device, and the device has to go through the function of updating that property, which for a developer, that's just a callback. Whether you're writing it in Python, C#, Java, whatever, you're doing a callback and you're saying, I've got this new variable, let me reintroduce it to my system. So that's why the reported and the desired can be different. And then you have the actual module identity properties. What's the name of the container, that kind of stuff. And all the security stuff that I won't go over because hopefully it's very secure. It's over my head a little bit. And then the module twin is what you see here. You have what is actually running on the device, and you have what is actually running on your back end with those desired and reported properties, and then those tags that you can manipulate. Also, I should note for desired and reported properties, the device can change those as well and send them back up so that you see different changes on the device properties, like overheating or something like that. So we talked about the edge agent, which is the management portion of the IoT edge. Now we're going to talk about the edge hub. So the edge hub is Azure's IoT hub Lite. So Azure's IoT hub, if I show you an architecture diagram of any of their architecture diagrams for IoT, there's going to be everything not in the cloud, IoT hub, everything in the cloud. Now they've got more products coming out that sort of sit there and run in front of IoT hub that encapsulate you from having to use it directly. But the architecture diagram is still the same. If it's outside of the cloud and it's a device, an IoT device trying to talk to the cloud, it's going through IoT hub in their architecture diagrams. The edge hub is a stripped down light version of IoT hub running on your device. So it doesn't support HTTP, it only supports MQTT and AMQP, both of the secure versions of those. And it secures the connection for your device. So it has the security chain and everything you need to have a secure communication between the devices in the cloud and the devices and the devices. And it optimizes the connectivity. If I had 10 devices in this room and we sent data up to the cloud, each 10 of those devices will send data whenever they want. If I have 10 devices and an edge gateway, and those devices connected to my edge gateway, and they all send it whenever they want, I don't have to write any code, but the edge gateway will start to batch those for me so that you're not sending each individual message. If 2 of them come in at the same time to the edge hub will batch those and send them up together. And the actual connectivity so that all 10 of those devices don't have an individual connection. And then it supports the module communication. So we've established that the modules running on the edge runtime are basically Docker containers. It facilitates those Docker communicators communicating with each other. So it routes the messages between the modules, it routes them to the cloud, and then it handles the offline storage. In case there's a delay, it handles the persistence so that when it's back on, it can send those messages where they need to go. So routing. When I want to set up all these different modules to work together, and by the way, I am building to a conclusion because you're probably sitting there thinking, I got a bunch of modules and there's this thing that communicate. So we are working towards actually getting all of that together, but I'm building the 2 different pieces and we're going to plug them together at the end. When I deploy a bunch of Docker containers to the device on the edge runtime or a bunch of modules, I have to route the messages between those modules. So the routing is literally a section of the document. It's a JSON section where you write all these different, you write from. So from this module, so I've got a module. Let's say it's a temperature sensor module. It handles communicating with the actual peripheral that's pulling in the temperature data. I'm going to say from that module, so it can have just the module ID. I can say just the temperature sensor module, or I can have specified outputs, so named outputs. I can say that this is the temperature data, this is, I don't know, humidity data because it has multiple different outputs. The where clause is, as you know, in any of these what a where clause is, right? So where it's not defined, or where you can actually read the body of your messages. If they're JSON messages, you can say where the temperature is greater than 50. You can do whatever you want in your where clause to determine if this route is used for this message. And then finally, your into. So I'm going to say where it's from, I'm going to say if it applies, and then I'm going to send it into. So I can send it into these other modules. I can actually route from the temperature sensor, in this case, to the different modules, and they can consume that data, or I can route that temperature data correctly to the cloud. Some examples. If I just say /* for the from, I'm saying for every message on this device. For /messages, all the device to cloud sent by a device with no output, through some or no output. You know, I don't think you care, because I got to get to the part. We'll go over the where clauses. You can look at system properties, application properties, and body properties. So you can look at what the module's name is. You can look at any of the properties set by the system itself. You can look at the properties that you put into it before you send the message, or you can look at the actual body of the message. All right, so system properties could be the content encoding, it could be the content type, it could be the connection module ID. These are things that are set by the system when it sends. And the application properties are things that you set. It's just a dictionary of string value pairs, right? So what the name of the value is and what the actual value is. And then you can actually inspect the body. So it's a JSON object, and you're writing this query to look at the body. I'm pretty sure everyone could figure that one out. But you can use that in your where clause. And then finally, the into, you can either pick upstream or brokered import. So upstream goes to the cloud. Brokered endpoint is another module. So I'm just going to go through that, because this is what I wanted to get to. So let's take that example I've been talking about of a temperature sensor, or a sensor of any data, right? So in this case, we've got a module that handles the hardware. So we've got a container that actually talks to the temperature sensor and understands how to actually pull the data off of the sensor itself. Then I've got a function. So if you know what an Azure function is, you can actually write Azure functions for the edge. I've got a function that's made to process those temperature sensor data points. And then finally, I've got my IoT hub, which pulls the data into the cloud. And for this example, the temperature sensor generates the data, and that gets routed into the edge hub. So the edge hub then sees that message, and we've written it so that all the temperature sensor messages get routed to the function. So now I've got code written for that function container to read that message, and it actually generates a message on whatever, like if temperature's over a certain value. And then that message gets sent back to the hub in the routing, because now I've got a new message. So this is a whole new event. And then that's going to get routed up to IoT hub and absorbed into the cloud. Hi. So let's go for another example, which is, let's do, don't start yet. Let's use the vision, right? So vision's a really cool one. Right now, a customer of mine is working for a very large retailer who has been mentioned in the Microsoft Azure space for a while, since they signed a big deal. That's the biggest hint I can give you. So they're a big retailer, and if you go into their stores right now, at least in the US, when you walk to checkout, there's literally this giant TV in the self-checkout area, and it's just the self-checkout area, and it draws green boxes around people, like showing you that they see people moving around. I don't know why it's there, but they've got the big TV, and that's what it does. It draws the green circles around people from that camera feed. They've gotten to the point, because the customer, what we used to do is we sold equipment that allowed to, if you stuck your hand in the aisle, or in the aisle or whatever, and you took an item out, there was a sensor there that would say, hey, an item just got, or I detected some motion, something just happened on here, and they would log that. By the way, they log everything. But they would take I took something off the rack data, and they had hardware for that. And now they're like, oh, we don't want that anymore. We want every aisle to have a camera on it. And every aisle will actually detect, using the video feed, the number of people, what they're doing, and if they're taking things on or putting them back on the shelf. So to accomplish that on the edge, what we can do is we can have an edge runtime that can take in video data. And then we can create containers that then process that video data. One, let's just create a container that can, from the Cognitive Services Custom Vision Service. We can create a container so that it can process each frame and try to make a decision. And then we can have multiple Azure functions that are also ready to receive different forms of data, one being an Azure function that processes the image directly. But coming out of the Cognitive Services container, I've taken the video data, and what I'm going to do is I'm going to transform it into a smaller message. Maybe I take that data and then just extract the information off of it. So let's just create a JSON document that says people, positions, and activities. And then from that, I can decide if that's something I should log locally, something I should immediately alert the cloud about through another function. So I've got the video data. So a new frame comes in. We're going to send that to now 2 different containers to process. I've detected a face in one, so now I'm going to take that face data and send it to that function that hasn't been used in the workflow yet. That function then processes that face, extracts even more data, and now I'm going to ship that data up to the IoT hub to absorb it into my cloud. So now instead of trying to stream data from all these cameras directly into the cloud and then processing it, using the edge, the Azure IoT Edge, I can now just process all of that on the edge using some of the same stuff I would process it in the cloud. And now, I mean, I don't care about if there's an empty aisle for an hour and a half, it's pointless. But if you stream that directly to the cloud and you get the bill for that, it's one of those conversations. You know, someone's messaging you on Slack or whatever, and then all of a sudden there's a call and you have to deal with it. At this, there's not that. It's all running on the edge, and you're not having to pay for it by the hour. Now, I will say, I got you in the idea of how computationally complex this is. For this particular use case, there's an entire data center in that store in the back running multiple graphics card server racks to actually process all of this data. So I'm hoping that helps you understand what the purpose of this is, why those containers exist, and why we have to route the messages between those containers. Is that helping, or should I go back? Are you awake? I mean, where are we? All right, good feedback. All right, so you have different edge gateway types. You can have a transparent gateway, you can have a protocol translation gateway, and you can have an identity translation gateway. So the different type of gateways are, so in this case, I've got a bunch of devices we were connecting directly to the cloud, and this is the one we've talked about before. Now I've got the Azure IoT Edge Runtime as my gateway, and then when I send those messages into that gateway, they get filtered, as you saw in the previous one. Now for the protocol translation, that's the one we also talked about. Got these old oil and gas companies with pipelines that were built in the 70s. They run SCADA systems, Modbus communication systems, or things that were just custom protocols. The protocol translation then takes those in, translates them, and sends them up to the cloud. In this case, the cloud doesn't know about each individual device. But in the identity translation one, the actual devices are individually identified in the cloud so that when you look at it through your gateway portal, you see each individual device. So I've been setting you up for all this, just this conversation around about where does the Azure IoT Edge runtime. So let's talk about the Tier 1 support, and I updated this like a month ago, so hopefully they didn't change it. Tier 1 support. The only ARM-supported operating system in Tier 1 is the Raspbian Stretch. That's the only ARM-supported operating system in Tier 1. Everything else is the AMD 64 supported. And those are all your, what do I call it, bulkier, right? Those are all of your more industrial or enterprise operating systems. When we think about Raspbian Stretch, we know we're going to be on something like a Raspberry Pi or just the Raspberry Pi. And you're not going to be able to process near as much as you can if you're on the Ubuntu servers or the Windows, either IoT or 10. Now, I will say specifically, these are a long way off from ever supporting ARM. And that's because Windows for ARM, or actually all of these, because Windows for ARM does not support containers yet. So all that special work they did to make sure containers run for Windows has not been ported to their support for the ARM hardware. And then Tier 2 is all your Linux, right? all your Linux and maybe an RTOS. So you've got CentOS, Debian, Ubuntu, Wind River, and Yocto. Has anyone here used Yocto? If you ever feel like, Julie Lerman, I went to her talk earlier, she talked about learning things, and like it's interesting. Yocto is one of those things that if you ever get a chance, it's how you build a custom Linux image through all these different build systems so that you get the stripped down version of exactly what you need. So if you ever want to waste a whole bunch of hours, check out Yocto. All right, and then the actual use cases, as we've gone through this, you've got edge analytics, just like that video processing to detect faces, or I want to detect aggregate information. You've got downstream device isolation. These are no longer connecting to the internet. Only the gateway connects to the internet. So now my devices have an extra layer of secure, or at least isolation on them. The connection multiplexing. Only one connection to the cloud where it handles how it sends the messages is much more efficient, especially if you get into large-scale deployments. Or in my case, where we're like in an oil and gas field where the only connection out in the middle of nowhere is some RF tower they built 40 years ago, and it's nice to be able to get the connections limited down. Traffic smoothing, so if there's an event, like I was talking about the temperature in here, I don't care. Like, tell me when it changes. I just don't care to know that it's whatever it is in here every second. So you can smooth the traffic by limiting it. You can also smooth the traffic when there's a high volume event. Northrop Grumman was I think it was Northrop Grumman. So they did testing for their airplanes, and they were doing shear testing. So how much force could it take for the wing blew off, and they were generating a terabyte a second to upload into the cloud. So they needed some sort of rate limiting whenever they were doing that testing. Or excuse me, not rate limiting, or traffic smoothing. And then there's the offline support. If I've got an oil pump in the middle of nowhere and a single cloud rolls in that destroys all communication, it has to run without being able to talk to the cloud. Okay, I wanted to look at the code, but I've rambled for too long, so we're going to skip looking at the code. My apologies. It's great. Go get the Azure IoT Edge extension for Visual Studio Code, and it pretty much does everything for you. Just look in the command palette, and it says create a solution, create a module, all of that stuff. I'm going to run through cognitive services really quick, because I am very low on time. All right, so cognitive services is broken up into 6 different sections now: vision, speech, language, knowledge, search, and labs. We're going to focus on vision for this one. I haven't actually had any use case for knowledge and search. Search used to be branded as Bing search, so I've never used it. And the same thing with knowledge. And then labs is a new thing they've come up with so that you can have these isolated environments to check out. So within Vision, we've got the Custom Vision API, the Face API, the Emotion API, the Video API, the Content Moderator, the Custom Vision Service, and the Video Indexer. I would have gone over all of those, but I'm out of time. We're going to look at the Custom Vision Service because it has integration with Azure IoT Edge. The main integration point being, I can tell it, I need a compact model that's better to run on the edge. So I'm going to lose fidelity. I'm going to have less accurate predictions, but I am going to be able to run it faster on the edge. So let's just take a look at that real quick. Okay, so I did this one. You can download the I forget the name. There's a specific data set of cats and dogs. Right, and so that's what we're building. We're going to build a model to detect whether it's a cat or a dog. I've had a use case for this, a similar use case for this, because someone told me they would really like something because they have a cat and a raccoon keeps walking up to the door, and they wanted something automated so that it would let the cat in. So in this case, we're going to try to detect whether it's a cat or a dog, and it's simple as this. If I click Add Images, and I go to my data set, let's say I go to cat, right, and I select... Let's not get too crazy. I actually did get too crazy there. This data set has like tens of thousands of cats and dogs, or hundreds of thousands, I think, actually. So I'm just going to upload some cats. I'm going to tag them as cat. I may have already uploaded these, and it'll detect duplicate images. So I upload my cats. I've uploaded the dogs already. So when I uploaded dogs, I just tagged them as dog. So I've uploaded cats, tagged them as cats, uploaded dogs, tagged them as dogs. Now, I'm going to click Train. When I click Train, it's going to take all those data sets and try to build a regression model. for the cats and dogs. Once that's built, I get a prediction URL. So with that prediction URL, I can just use that URL. There's an API generated. I can send it an image, and it'll send back cat or dog and other information with that image. All right, so with our new model, I can also go, oh no, I picked the wrong training type. So if you have the right training type, see if I can get this done in time. Yes, things have changed. Oh, save changes. So if you use, and that's as simple as it is to actually change your training type. If you actually train for the compact version, it is made to export. So not only can you export it to run on the edge, you can actually just export it to run in your data center. You're going to get multiple options, and then you can set up your own API in your data center to consume these images without having to use cognitives or without having to use the custom vision service. So once this is done, I can just click export. And then I can pick between CoreML, TensorFlow, Onyx, and a complete Docker file that I can take and then run either on the edge. I can run it on Android. I can run it on iOS. And it's as simple as, let's just download the TensorFlow one. You have to write your TensorFlow code because it doesn't know if it's going to Android or Python or whatever. They do have sample code for you, but there it is. It gives me my labels. So, cat, dog. And it actually gives me my model file that I can then use in my TensorFlow to hydrate and create an API to pass images to and get cat, dog back out on the other side. So sorry that we had to speed through the last few portions of this to get to the custom vision service, and we skipped over the actual code for the Azure IoT Edge. However, this being a .NET conference, I can't use my normal excuse. For Azure IoT Edge, you can write modules in Java, Python, JavaScript, C, C++, and .NET Core. My normal excuse is, well, there's too many variations, so I don't have a lot of code examples. I don't know if you'd be Python or .NET. In this case, I know you're all .NET, but that's a lot of work. But it's there. You can go and you can download the .NET Core if you use the Azure IoT Edge, and you can create a new one, and it's they've got all different types of ways to make them. So for learning resources, if you want to learn more about machine learning, I suggest this book. I read this book when I got stuck traveling India with no internet for 2 weeks, and this was an amazing book. Pretty much everything I know about machine learning started here, and it makes it so easy to actually get started, because when I thought of machine learning, everyone did the demo I did, where there's this deep learning neural network and all these weights and trainings. It is so much simpler. If you don't have anything that needs deep learning feature sets, you can just use something as simple as a decision tree, and it'll literally print out, after it looks at your data, the tree that it makes to make its decisions. These slides will be available. They're available on my blog. Whatever update has for me to make these available, I'll make them available. But here's some more learning resources if you'd like to use them. And then finally, thank you for coming to my talk. If you need to contact me, here's my contact information. If you have any questions, I'll be outside.